Hi, this is a presentation for paper submitted to IEEE Sensor 2020. My name is Yiqi, I'm an engineering master's student in Fraser University. The title of our paper is Measurements of Microphone Array Phase and Amplitude Behavior towards Controllable Beamforming. Thank you for attending this session.
The concept of beamforming was developed and well studied in antenna systems. In this paper, we adapted beamforming to miniature compact acoustic systems. The questions discussed are, how can we physically evaluate their phase and amplitude? Also, can the reflector alone be used for miniature microphone arrays? So we presented a procedure for physically measuring the phase and amplitude of arrays using a two-port audio analyzer. Beamforming, which is described as the physical displacement between the elements corresponding to phase differences between the element signals. The response or pattern acts as a spatial filter for the propagating signals. The physics of acoustic waves is very different to that of electromagnetic waves. However, the signal processing concepts are similar. In antennas, omnidirectionality is only possible in one pattern cut. The transmit and receive responses are closely related through the reciprocity of most types. From the signal processing view, antenna arrays normally operate over a small relative bandwidth, and there is no physically moving parts. Different from antennas, in acoustics, a standalone omnidirectional element is possible, and the reciprocity are more complex over an extremely large bandwidth. Also, sound waves are elastic waves and propagate through vibrations of a material medium. For antenna array, mutual coupling is well studied and fully understood, but there is very little literature on the mutual coupling in acoustics. Figure 2 here shows a cross-section of a two-element microphone array. The analytical phase differences are calculated from geometric principles as given in these two equations here. The measurement environment setup is given in Figure 3. These measured phase differences and the geometric modeled ones are shown together in Figure 4 for comparison. It can be seen that the measured phase differences are a reasonable fit to the modeled values. Amplitude are expected to be identical for omnidirectional microphones ideally. However, in Figure 5, the amplitude vary on different rotation angles theta, also more sensitive to a 2 kHz frequency. The measured amplitude cannot be considered as ideal, and beamforming would be affected by their large variations across the sampled frequencies and angles. To conclude, our method presented estimates of embedded microphone directional response samples. It shows that while the relative phase can behave similarly to that of isolated, for electrically small sensors, the amplitudes differ, which compromise accurate beamforming. In summary, there is a significant gap for estimating a real-world acoustic microphone array response, and for accurate beamforming, the reflector alone cannot be used. These are the references included. Thank you for listening.